In this video, we'll take a look at how to solve the work energy practice problems from our assignment in class. First of all, with the work energy theorem, I think it's important to point out that there are often multiple ways to solve a problem, multiple approaches that are equally correct. So if your work doesn't look exactly like mine, but your answer does, there's a pretty good chance that you did it correctly. But if you're ever unsure, be sure to ask me in class and I'll let you know if what you did works for every problem that you would try. In question 1, you're asked to just calculate total mechanical energy. That's a really important concept for all of these work energy theorem and conservation of energy problems, that the mechanical energy is the total of an object's potential and kinetic energy. So we can solve for each of those individually and then add them up together, or written out as a big long thing, it looks like this: mgh plus 1/2 mv squared. And all the variables that we need are given to us in the problem. We're given the mass, 25 kilograms. We're given the velocity for the kinetic energy part, and we're given the height above the ground for the potential energy. So if you plug all those in, along with our good friend little g, 9.81 meters per second squared, you should get an answer that totals up to 6,700 joules of mechanical energy. In question 2, we're asked to figure out the height of an object that's experienced some amount of work that's been done. We're told that the potential energy at the start is 150 joules, and that we're going to do 450 joules worth of work on that object. Since work is equal to a change in energy, if you start with 150 joules of energy and you add 450 joules of work, you're going to end up with 600 joules of total energy. In this problem, even though it doesn't state it clearly, there is no velocity, or certainly no change in velocity that we need to be concerned about. So the kinetic part of mechanical energy isn't really relevant. That makes this 600 joules of mechanical energy all potential. And that potential energy is what's determining the height. So if we take a look at how that gets finished off, 600 joules of potential energy equals this object's mass, 6.5 kilograms, times little g, 9.81 meters per second squared, times the height that we're solving for. So we solve by dividing by 6.5, divide by 9.81, and when you've done all that, you should get a height of 9.4 meters total when you're done. For question 3, you're asked to figure out the work that's needed to cause a change in velocity from 5 to 10 meters per second. When you're asked to figure out the amount of work done based on some velocities, what that's really telling you is that the kinetic energy of the object has changed. It's gone from a kinetic energy based on a low velocity to one based on a slightly higher one. So there are some mathematical ways we could write this, but I think the simplest way to approach it is just with the concept that work is equal to a change in mechanical energy. And in this problem, there's no height changing. So all the mechanical energy is really kinetic. So work in this problem is equal to a change in the kinetic energy, which means that work is equal to how much you finish with, 1/2 of mv squared final velocity, minus the work, or the kinetic energy you started with, 1/2 mv squared based on the initial velocity. So for this problem, we'll keep the mass the same for both. It's 35. And start with the final velocity of 10 meters per second. That number is squared. And we'll subtract from that 1/2 of the mass times the initial velocity squared, which was 5 meters per second. When you do that, you get 1750 as your final energy, 437.5 as your initial energy, and the change then was 1,313 joules, going from 5 to 10 meters per second. Question 4 is a continuation of number 3. If the amount of work done, that's 1,313 joules, covers a distance of 26 meters, how much force was applied? And this is the case where we can use the other definition for work, that work done is a force times a distance. So that 1,313 joules of work is equal to how much force was applied over the distance of 26 meters. And this works out when you divide 26 into both sides to be a force of 50.5 newtons. Question 5 asks us to figure out the acceleration of that object, and we have a lot of different ways to calculate acceleration, but the one that's going to work for us here is Newton's second law that says acceleration is a net force divided by a mass. So if we know that the net force acting here was 50.5 newtons, as we had just calculated up here, and we have the mass from problem 3 still as 35 kilograms, the acceleration has to equal 1.4 meters per second squared. Question 6, we're given an object's experienced force and the distance over which that force is applied. We're also told the weight and asked to figure out the velocities. We've got a lot going on here. I think it makes sense to start picking it apart piece by piece. The first thing that I notice here is that we're given a force and a distance, 240 newtons and 15 meters. That to me looks like a work. Work is a force multiplied by a distance. So if you have 240 newtons of force multiplied by 15 meters of distance, the amount of work that's been done here is 3,600 joules. The other thing that I notice is that we're asked a question about velocity, and the easiest way to relate work to velocity is in a change in kinetic energy. So the amount of work that's been done represents an increase in kinetic energy. Our object had started at rest, so the initial kinetic energy is 0. We are interested in finding out what the kinetic energy is at the end, and we know that the change in kinetic energy is the work that's been done, 3,600 joules. So that means in order for this object to have experienced a change of 3,600 joules starting at 0, the final kinetic energy, KEF, has to equal 3,600 joules. That's going to be important for helping us find the velocity. Since that kinetic energy of 3,600 is equal to 1/2 of m times v squared, the only other thing we need to know to find velocity is the mass. And we're sort of given the mass. Not exactly, it's the weight, but it's pretty darn close. We can figure out the weight-mass relationship using our equation Fg equals mg, where we're told the force of gravity is 80 newtons, and we can figure out the mass from there. Total mass of this object is equal to 8.15 kilograms, and that is the number that needs to go up here into our equation for kinetic energy. So we have 3,600 joules equals 1/2 of 8.15 times v squared. We can solve then for v, and we get something like 29.7 meters per second. The last problem here involves a falling object, where we are first tasked with figuring out the total mechanical energy. This is just, again, the potential plus kinetic energy, where really the kinetic here is 0 because nothing is moving. So that's 0 plus mgh, where m is 3, h is 2, and g is 9.81. So multiply those three things together and you'll get 59 joules of potential energy. In part B, we're reminded that gravity is an internal force. It doesn't change the total mechanical energy of an object. So as a result, when this object strikes the ground, its mechanical energy is still going to be 59 joules. Only now, instead of having 59 joules of potential energy, it has none. No potential energy because its height has been reduced to 0. That means if there isn't any potential, all of this mechanical energy must have been converted into kinetic energy, energy of motion, based on how fast the object is moving. So the answer to part B is 59 joules, and the reasoning is the conservation law for energy. And once we know the kinetic energy, 59 joules, we can figure out the velocity using 1/2 mv squared. Incidentally, if you wanted to, you could also calculate this velocity using our kinematics equations because you know how high up the object was and the acceleration due to gravity. But in this unit, you probably want to get more accustomed to the work energy concept. So solve this, divide both sides by 1/2, divide by 3, square root all of that to get a velocity of 6.3 meters per second. And finally, we're asked if the book was dropped from 4 meters, what would the impact velocity be? So we're doubling the original height of the object from 2 to 4 meters, which means we have a new potential energy that's based on the mass times g times the height of 4 meters. And that potential energy is 118 joules. As you might expect, it's twice as much as it was when it was only 2 meters high. And this potential energy is still equal to the kinetic energy at impact for the reason that was explained in part B. So now you have an object that has 118 joules of kinetic energy, and that's equal to 1/2 the mass times v squared. And when you solve for v, you get 8.9 meters per second.